Welcome to Review Lecture 1.4, Coulomb's Law. You should be able to apply Coulomb's Law to determine the electrical forces between charges, apply the shell theorem, and apply the superposition theorem. Okay, now Coulomb's Law for charged particles or objects that are small compared with the distance between them. The electric force between the charges varies directly as the product of the charges and as inversely as the square of the distance between them. So mathematically, F equals 1 over 4 pi epsilon naught times the quantity Q1, Q2 divided by the just R squared. We can rewrite that as K times Q1, Q2 divided by R squared. R is the distance between the charged particles. Q1 is the quantity of charge of one particle. Q2 is the quantity of charge of the other particle. Epsilon naught is the permittivity constant. In vacuum is 8.85 times 10 to minus 12 Coulomb squared per Newton meter squared. K is the electrostatic constant. It equals 1 over 4 pi epsilon naught. Also equals 8.988 times 10 to the 9th Newton meter squared per Coulomb squared. Now notice there are absolute value signs around the charges because we don't want to use that to determine the sign on the force. Instead, what you do is you use this to determine the magnitude of the force and use the likes attract opposites repel rule and a force vector diagram to determine the force directions. As a reminder, checkpoints should be done at home in your notebook before you view the videos or come to class. The charge on sphere 2 is twice that on sphere 1. Which vector below shows the force of 2 on 1? Now, the thing you want to look for is the direction. So, for instance, remember Newton's third law, equal and opposite. So anything that is not opposite, you eliminate. So immediately you get rid of D and E here. Then this has to be the same length roughly as one of these. And B is the closest answer here. So yes, it's B. The charge on sphere 2 is twice of that of sphere 1. When the distance between them is R, the force of 1 on 2 is F. Which vector below, drawn the scale, shows the force of 1 on 2 if the distance between the spheres is reduced to 1/2? Well, if it's reduced to 1/2, it's going to be 4 times as much. None of these look like it's 4 times as much, so I would say none of the above. Remember, it's an inverse square law. Now, two important observations and warnings regarding Coulomb's law. Coulomb's law applies only to point charges or approximately to objects whose size is much smaller than the separation between them. This is especially important when the objects are conductors because the charge can move on conductors. So be very careful with Coulomb's law and conductors. Unless they're point charges, I wouldn't do it. The electric forces that are vectors actually can be superimposed, that is added vectorially. They're forces just like any other forces. If multiple charges are present, the net electric force on them on charge J due to all the other forces is the vector sum of all of the forces put together. Okay, now there's some problem-solving strategies. One of the things I always try to get students to understand is there's a certain strategy for solving problems. You should do it pretty much following this strategy. Read everything carefully. Write the problem down in your notebook, including the problem statement. Note all the givens and knowns with the units. Draw a diagram showing all the pertinent particles' positions. Say that fast 5 times. Whenever you get stuck, reread the problem. You may have forgotten something. I've been teaching for many, many years, and I used to give tests in class, face-to-face class, and give them in class. And students would come up to me during tests, and they come up and they ask me, I don't understand question 4. And most of the time, they hadn't brought their test up to me, and I don't memorize the test. Right? Go back and get your test. Bring it back up here. I don't memorize these things, so they bring it back up, and I said, okay, what problem were you stuck on again? Problem 4. I deliberately did this because I wanted them to slow down and think. I said, okay, bring it around here. Show it to me. I put it in front of them, and I point onto the problem as I read the problem aloud. About 40 to 50 to 60% of the time, the light bulb would come on. The student would say, oh, they hadn't even read the problem. Instead of reading the problem rereading the problem when they got stuck, they just got stuck and just churned. So whenever you get stuck, reread the problem. 9 times out of 10, that'll solve your problem. And it certainly won't hurt anything. Now identify the physics of this. Identify point charges or model objects as point charges. Write down what the physics is. If it's Coulomb's law, say Coulomb's law. Make sure the objects are small in size relative to their separation distances, especially with conductors. Then you want to visualize what the situation is and draw a diagram. It doesn't have to be anything fancy. You don't have to get out a protractor and ruler and make it scale. You can make it approximately scale. Use the pictorial representation to establish a coordinate system. Whenever possible, place a coordinate axis along a force vector. This will simplify the math. Show the positions of the charges, show the force vectors on the charges, define distances and angles, and to identify what the problem is trying to find. You can't get to a location unless you have a destination. Now solve. The mathematical representation in this case is based on Coulomb's law. Sketch the directions of the forces on the vectorial representation. When possible, do some sort of visual or graphical vector addition on the pictorial representation. It doesn't have to be fancy. You don't have to get out the protractor. Just that, okay, well, this force, I got these three forces adding up. The resultant force is going to be in the north direction. Something like that is good enough. Write each force vector in terms of its x and y components using cosines and sines. No, you can't get away from vector addition here. Add the components to find the net force. Then you want to assess and check your work. Check that your result has the correct units and significant figures. Is it reasonable? Does it answer the question that was asked in the problem? Reread the question, make sure you've not missed anything. Now, these are general strategies I'll go over in every single problem and that I do as a demonstration in this class. I actually put these down. So you're going to see this over and over again. The first couple problems we will do in the lectures, I will show them as full demos. After that, the lecture slide PDFs that you will get on Blackboard will not have the full demo on them. They'll just have the problem statement. That means you're supposed to do those at home before class or before you review the video. Remember, the video and the class is the review, not the first time you see the material. Okay, and these checkpoints should be done at home too before you view the video or come to class. Which is the direction of the net force on the charge at the lower left? So we're looking at all these different charges and what is the direction on this charge? Now, the first thing I always want to do is eliminate anything that's crap. First of all, these are all positive charges on a positive charge. So you know it's not going to be D because these charges are going to repel each other. Now then I start breaking it up. Okay, this one is going to push that one in that direction. That's B. This one is going to push in direction C. That one's going to push in direction of A. These two are equal. And if you add them up, sort of mentally, it's going to be along this direction, along B. They only asked for direction, not magnitude, so I'm not worried about the length of the vectors. It ends up being B. What is the direction of the net force on this charge at the top from the two at the bottom? Now, again, I do the same thing, okay? These are going to repel, so these are going to have a direction along their line, joining them outward. Okay, so somewhere between A and D. This one is going to attract to that one. So the direction of the force is going to be along the line, joining them, and it's going to go in the direction toward minus Q. So we got this one plus this one. They're roughly equal to each other, and the y components are going to cancel out and add up to be along line D. There we go. So here, as I said before, here's this vector, here's that one, it adds up to make D. Coulomb's law versus Newton's gravitational law. They actually look alike. They're both inverse square laws. They act a lot alike too. There's only one major difference between them. One of them is purely attractive and the other one is either attractive or repulsive. So Newton's law depends upon the product of masses. Coulomb's law depends upon the product of the charges. Newton has an inverse square law on distance between the bodies, but Coulomb is also an inverse square law on distance between the bodies. But Newton's law is only attractive. Coulomb is either attractive or repulsive. Newton's law, very weak. It's the weakest of the four fundamental forces. Electrical forces are very strong. It's a conservative field force. Gravity. Coulomb is also a conservative field force. And the constant G in Newton is very small, 6.67 times 10 to the minus 11th. And the constant K for the Coulomb is very large, 8.99 times 10 to the 9th. But they look alike. And they behave alike. They're inverse square laws. The electrical force between any two objects obeys a similar inverse square relationship with distance as gravity does. The relationship among electrical force, charges, and distance, Coulomb's law, was discovered by French physicist Charles Coulomb in the 18th century. The SI unit of charge is the Coulomb, abbreviated with a capital C. A charge of 1 Coulomb is a charge of 6.24 times 10 to the 18th electrons. Now, to get an idea of the scale of that, a Coulomb represents the amount of charge that passes through a common incandescent 100-watt light bulb in about 1 second. It's actually, since a 100-watt light bulb, I think, draws 0.83 amps, it'd be about 1.2 seconds. Okay, now there's a proportionality constant in this. The proportionality constant in Coulomb's law is similar to G in Newton's law, but it's much larger. So K is 8.988 times 10 to the 9th Newton meter squared per Coulomb squared. If a pair of charges, 1 Coulomb each, were held 1 meter apart, the force of repulsion between the two charges will be almost 9 billion newtons. We can derive that by saying just putting 1 Coulomb in each of these and holding them 1 meter apart. The force of electrical repulsion is 8.988 times 10 to the 9th newtons, which is about 9 billion newtons. This would be more than 10 times the weight of a battleship. It's kind of amazing, isn't it? By contrast, if you held a pair of 1 kilogram masses 1 meter apart, the gravitational force on them will be very tiny. Plugging it into Newton's gravitational formula, it ends up being 6.67 times 10 to the minus 11 newtons. Gravity is only large when the masses are large. Electrical forces can be considerably much larger than gravity. Because of this, these forces are very strong. Because of this, it's extremely important that the electrical forces acting on you balance each other. That's cancel out and have no noticeable effect at all. Otherwise, matter would either collapse or else basically fly apart. It'd be all kinds of problems. Okay, it's a good thing that the normal state of matter is neutral, where the charges balance and cancel each other. Otherwise, we wouldn't even be here. We depend on this for life. Our universe would be unrecognizable without this situation. Okay, here's an example. A charge of Q1 equals 4 microcoulombs is positioned at the origin. A charge Q2 of 9 microcoulombs is positioned on the x-axis at a point of x2 equals 4 meters. Where on the x-axis can a negative charge Q3 be placed such the force on it is exactly 0? Is there any place off the x-axis where the force on Q3 will be 0? The first thing you want to do with this type of problem is write the problem statement down in your notebook so you know what it is, because you think you're going to remember it. Guess what? A week later, you don't remember it. So write it down, because that's the way we remember things. That's why writing was invented. Write down the knowns with the units on it. This is a good time to take note of those units, or you're going to have to convert to SI units, because if you don't do that, you're going to wind up getting messed up. So Q1 equals 4 microcoulombs. Here's, of course, a units trap. X1 equals 0, Q2 equals 9 microcoulombs, another unit situation. X2 is 4 meters. We want to know the electrical force on a third particle from the first one. We want that force to be 0. The physics of this is Coulomb's and Newton's laws. We're going to pick a coordinate system of the origin at Q1 to make it easy on ourselves. We're going to draw a free body diagram. We need to find equal and opposite forces from the outer charges on the middle one to balance. That is, sum up to 0. The only place is on the x-axis. You can see if you move this particle off the x-axis, it's always going to pull back down to the x-axis. So the answer to the second question is no. Any place else will not be stable because the forces will not balance. In fact, it will pull the particle down to the x-axis. Now that we've solved that question, we're going to place Q3 between the first two charges as a distance r1 from charge 1. It doesn't matter if the new charge is positive or negative. Actually, it doesn't make any difference. You can still find a balance point between them. The distance between Q3 and Q2, which is this distance here, is now 4. That's the 4 meters minus r1. So we want to write down the knowns, and we've converted them into SI units. We want to find R1. So we apply Newton's first law, which is summation forces equals 0, and Coulomb's law, such that F equals K Q1 Q2 divided by R squared. And the forces had to balance. So this means that K Q1 Q3 divided by R1 squared is going to be K Q2 Q3 divided by the quantity 4 minus R1 squared. We're going to cancel out K and Q3 from both sides. Now, whenever you do homework problems or any kind of problems, solve them in terms of the symbols first. Don't get the calculator out yet. Do it by symbols. Why? Notice K and Q3 cancel out from both sides. This means you don't need to know Q3. Now, on test questions, I love to do things with students. I give them a problem like this. I don't give them Q3. All of my tests are multiple choice. And one of the wrong answers at the bottom with this would be can't tell without knowing Q3, because I want to catch people who don't solve it symbolically. I want you using symbols. Now, there's another reason for that. Not only does some of this stuff cancel out, so this means you can solve problems that maybe you would not have otherwise thought you could solve, and you can simplify problems, which makes them easier to solve, but it makes the physics clear. You see that Q3 doesn't matter. It doesn't matter what its sign is, and it doesn't matter the magnitude of the charge. So this is why I want you using symbols. On top of this, if you get another problem like this, you can reuse it if it's symbolically written. You can't do that as easily if you plug the numbers in. Now you plug in the numbers. And in this case, 9 times 10 to the minus 6 coulombs with the units on them times R1 squared, that will be in terms of meters squared, equals 4 times 10 to the minus 6 coulombs times the quantity R4 minus R1 quantity squared, meters squared. First thing I do is I check out the units. The units cancel out on both sides. That means they're equal, okay? Because the units have to be equal or equivalent on two sides of an equal sign. If they aren't, you're in trouble. Now, we reduce this. We notice that these are all terms of squares. We can reduce this by taking the square root of both sides, and we take into account both roots. Plus or minus 3R1 equals plus or minus 2 times the quantity 4 minus R1. And in this case, the negative root makes no sense because it'd be over here somewhere. So now we know that the negative charge must be between these two positive charges, somewhere between x equals 0 and x equals 4. We're going to expect it to be closer to the smaller charge. And it turns out it is. R1 is 1.60 meters, and we ask ourselves, does this make sense? Yes, it does, because it's closer to the smaller charge. That's the kind of thinking and work I want to see on your homework problems. If you do it this way, I guarantee you'll get a much better grade than if you do it in a typical student method, which is to find a piece of scrap paper or just stick it on their calculator, or worse yet, their phone. If you don't have a good scientific calculator at this point, please get one. 2 balls with positive Q charge and negative 4Q are fixed at a separation distance of 3R. Is it possible to place another charged ball, Q naught, anywhere on the line between the charges such that the net force on Q naught will be 0? Now, this is one of those ones you eliminate possibilities. Okay, so eliminate all the crap, and whatever remains, no matter how improbable, is likely to be the truth. So first thing I do is I start checking things. I'm going to take a positive charge here. I stick a positive charge here. If I stick a positive charge here, what's it going to do? It's going to run away from this one and go toward that one. They only ask for between the two charges. So no, I can't put a positive charge here. Then I'm going to try a negative charge. If I try a negative charge, the opposite's going to occur. It's going to run toward this one and get away from that one. So no, I can't have a negative charge. So I can eliminate yes, but only Q naught is positive, yes, but if only Q naught is negative. We can also eliminate yes that's independent of the sign or value Q naught. The answer to this one is no. The net force can never be 0. Net force can never be 0 on the line between the two charges. The forces will add, not cancel. It also cannot be 0 off the axis between the two charges. However, it can be 0 somewhere outside on this line, but either to the right or left of the group of charges. Okay, so 2 identical non-conducting spheres are each attached to a thread and suspended from the same point. If the spheres repel each other such that the threads make an angle of 7 degrees from the vertical, what is the charge on each sphere? The mass of each sphere is 0.030 kilograms. The length of each thread is 30 centimeters. Now, when I read this, the first thing I see is a units trap here. You're going to want to convert all the units to SI. Write down your knowns. They're non-conductors. That's an known. The length I'm going to convert to meters right out the bat, 0.30 meters. The mass is already in terms of SI units, 0.030 kilograms. The angle is 7 degrees. The unknowns, what is Q? The physics of this is Coulomb's and Newton's law. We examine the situation. We note that there is a left-hand right symmetry. That is, identical balls, identical angles, equal forces, equal and opposite. This is a force balance problem between the tension, electrical force, and gravity. So in this case, I'm just going to pick one side of this. We're going to apply Newton's and first and third laws. Each ball experiences the same magnitude of forces in the x direction and opposite directions. We're going to use Coulomb's law to get the electrical repulsion force between the two charges. And we draw a free body diagram of just one of them because this is a symmetrical situation. We only need to know one half of this. So in other words, here's the tension in the string. Here's the electrical force pushing this one this way. And here's the weight that's trying to pull it back down again. Okay, I've repeated the knowns and unknowns up at the top here. We're going to break the forces just like we did before into x and y coordinates. We're going to use Newton's first law, summation forces equals 0, to balance the forces in the x and y direction. We also know from trig that R equals 2 times L sine theta. In the x direction, we have t times the sine of theta equals Fe. In the y direction, we have t times the cosine of theta equals mg. And we still have trig R equals 2L sine theta. We can combine equations. If you take the sine and divide it by the cosine, you wind up with the tangent. So t sine theta divided by t cosine theta, and of course the t's will drop out, you wind up with tangent theta. That will equal Fe divided by mg. And then we can substitute in here. So we wind up at F equals kq squared divided by r squared. And that's just from Coulomb's law. That has to equal kq squared divided by the quantity 2L sine theta squared. We can combine and end up with this here thing right here. The square root of the quantity mg tangent theta divided by k times the quantity 2L sine theta. Now at this point, we're ready to start plugging numbers in, being careful with units and writing the units down so we know that they're correct. I took this 2L sine theta. Here's 2 times L times the sine of 7 degrees. And then I took this one here that's under the square root sign and wrote it in these curly brackets. So here's our mass of 0.03 kilograms. Here's our G of 9.8 meters per second squared. And of course, this is the units cancellation here to make sure all the units come out. Here's the tangent of the angle. And this is divided by K, which is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. If you check all the units, they cancel out and come out in coulombs, which is what we want. Don't forget to take the square root of the stuff that's in the brackets. When you do all of that, you wind up with Q equals 1.46 times 10 to the minus 7th coulombs, and that is 0.146 microcoulombs. Now, this is the way I want you doing problems. Why? Because this way works. Okay, now electrical forces in atoms and molecules. Most objects have an almost exactly equal number of electrons and protons, so the electrical forces usually balance out. Between the Earth and the Moon, for example, there is no measurable electrical force. In general, the weak gravitational force, which only attracts, is the predominant force between astronomical bodies. Although electrical forces balance out for astronomical and everyday objects, at the atomic level, this is not always true. In fact, the electrical attraction between the positively charged protons in the nucleus and the negatively charged electrons in the shells hold the electrons in their energy levels. Often, one or two or more atoms, when close together, can share electrons. Bonding results from the attractive force between the negative electrons of one atom and the positive nucleus of the other atom is greater than the repulsive force between the negative electrons of both atoms. Coulomb's law underlies the bonding forces between molecules that are essential in the field of chemistry and are essential to you as a living being. This is how you digest food and turn it into energy. And this is what holds all of your molecules together. If you are in a calculus-based physics class, such as Physics 222, you're responsible for this slide on exams. If you are in an algebra-based physics class, such as Physics 122, please skip ahead to slide 26. For calculus-based physics, such as Physics 222, you should be on slide 25. Okay, as with all forces, the electrostatic force is also a vector. The electrostatic force vector acting on a charged particle due to a second charged particle lies directly along the line joining the two charges and either is directly toward the second charged particle or directly away from it. The net electric force exerted on a charge by a group of particles is the vector sum of the force contribution from each charged particle. So the electrostatic force on a particle one can be described in terms of a unit vector r hat, I'm going to call it r hat, along an axis that runs through the two charges. In this case, where there are like charges involved, the force would be repulsive and directly away from charge 2. That would be the force on this one. For opposite charges, which is not shown here, this force will be reversed and be pointing radially toward charge 2. For algebra-based physics, such as Physics 122, you should be on this slide. As with all forces, electrostatic force is also vector. The electrostatic force acting on a charged particle due to a second charged particle is either directly toward the second charged particle, that is for opposite signs of charge, or directly away from it for the same sign of charge. But that force always lies along the axis joining the two particles. The net electric force exerted on a charge by a group of particles is the vector sum of the force contributions from each charge. So the electrostatic force on particle 1 can be described in terms of a force along the axis that runs between the two charges. In this case, these are like charges. It would be repulsive and radially away from charge 2. For opposite charges, which is not shown, this force will be directed radially toward the other charge. Coulomb's law, you can use superposition just like you did before. The electrostatic force factor acting on a charged particle due to a second charged particle is either directly toward the second charged particle for opposite signs or directly away from it for the same sign. If multiple electric forces act on a particle, the net force is the vector, not the scalar sum of the individual forces. So in other words, if you want to find the force on, say, particle number 1, you'd vectorially add the force on 1 from 2, plus a force on 1 from 3, plus a force on 1 from 4, all the way out to the number of particles you have. That would be n, plus a force on 1 from n. Now, there are two basic shell theories for electrostatic force. You may have encountered shell theories when you talked about gravity. Number 1, a point charge located anywhere outside a shell which has charge uniformly distributed on its surface is attracted or repelled as if the shell's charge were concentrated at the point at its center. Number 2, a charged particle placed anywhere inside a shell with charge uniformly distributed on its surface has no net force acting on it due to the charge on the shell. Number 1, in other words, when dealing with a point charge outside a uniformly charged shell, replace the charged shell with another point charge with charge equal to the shell's total charge located at the center of the shell. Number 2, a charged particle placed anywhere inside a uniformly charged shell will not be affected by the shell's charge, so you can ignore the shell. Warning, do not use this with closely spaced conductors because the charges on a conductor are free to move in the conductor and will not remain uniformly distributed when affected by a nearby charge. These are two identical charges hanging from pendulums, just like the problem we just did. Gravity causes the charges to rotate inward. As they approach each other, the electrostatic force increases and they push further apart. Field lines, which are in the next chapter, can be seen growing and shrinking as the gap increases and decreases. Here's an example. We're going to try to pick up a charged glass bead. Now, you should be doing these examples at home in your notebook before you come to class or view the videos. We have a small plastic sphere. This charge to minus 10 nanocoulombs is held 1 centimeter above a small glass bead at rest on the table. The bead has a mass of 15 milligrams and a charge of positive 10 nanocoulombs. Will the glass bead leap up to the plastic sphere under the Coulomb forces? We're going to ignore gravitational forces between the objects because these objects are very small. But we cannot ignore Earth's gravity on the glass bead because the Earth is a very large object, and also you wouldn't have a problem if you ignored that anyway. So the knowns are Q1 is minus 10 nanocoulombs, Y, the initial position, Y naught, is 1 centimeter, M2 is 15 milligrams, Q2 is 10 nanocoulombs, and the final position is Y1 equals 0. We need to know is F net, which is the sum of all the forces on this bead here, greater than 0. Physics of this is a force balance problem between gravity and electrical forces. To make the bead fly, we need to say that F net, which is F12 minus Fg, is greater than 0. Fg is the weight of the bead. That is m times g. F12 is the Coulomb force on the bead from the plastic sphere, and that is K Q1 Q2 or R squared. So we can rewrite this as K Q1 Q2 over Y1 minus Y naught quantity squared minus M2G is greater than 0. Or we can write this as K Q1 Q2 over Y naught squared is greater than M2G. If this condition is satisfied, then the glass bead will fly. If it isn't, then it's going to sit there on the table. Now at this point, we can put numbers in here, paying due attention to the fact that we have some units traps up here. So we have K of 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. Q1 is a charge of 10 nanocoulombs, which is 10 to the minus ninth coulombs. We're going to ignore the sign. And Q2 is 10 to the minus ninth coulombs. And the distance between them is 0.01 meters, and we're going to have to square that. If that is greater than the weight of the bead, which is 15 times 10 to the minus 6 kilograms times 9.8 meters per second squared, then the bead is going to fly. When we run the numbers, we find out that this over here, the Coulomb forces, which is 9 times 10 to the minus 3 newtons, is considerably greater than the gravitational force, which is 1.5 times 10 to the minus 4th newtons. So yes, the bead will leap up because the electrical Coulomb force exceeds the gravitational force. Thank you.